Journey, and thanks, of course, the organizers for giving me this opportunity to do this short review. Actually, there will be two topics in the talk. You discover the second half the way through. Since I'm the first of two with Georg after me talking about iron pnictides, I took care of a little introduction, even if I'll be actually rushing through it because time is short. So iron-based superconductors have been brought to big audience in 2008, and this is the timeline of the year 2008 as far as the discovery of these materials is concerned. And then it went on with other discoveries, but this is just to show the huge amount of different compounds raising quickly up in TC that has characterized the discovery of these materials and how many different families there are. Now, among the different families, the structures are varied, but there is one common block, which is the iron arsenic in the pnictides, iron phosphorus, or the iron selenium or tellurium in the chalcogenides. That's why the only remaining common thing is iron, and that's why they're called iron-based superconductors. Like in other names. Ironics has been christened at some point. It could be used. Ironics. Then the relevant block is this iron ligand buckled plane. It's a square plane of these red irons, but the ligands are above and below alternatively, so it's not completely bidimensional. And it's immersed in a tetragonal or orthorhombic symmetry depending on the phases. These are the different many phase diagrams of the different families that have been traced. I won't go through them, but I will highlight the common point, which is that almost, with the due exceptions, but almost in all of them, you have a magnetic, an antiferromagnetically collinear antiferromagnetic phase going down with some chemical substitution, be it carrier doping or isovalent doping, and leaving the place from this magnetic and orthorhombic phase to a tetragonal paramagnetic metallic phase at high temperature and superconducting, which becomes superconducting at low temperature. There are some due exceptions. For instance, in some chalcogenides, the magnetic phase is absent, but the physics is indeed similar. Then, since we are in a workshop on Mott phenomenon, bad metals, and etc., it's worth asking from the outset, what is the role of electron correlations in these materials? And of course, this was one of the big questions around. There are contrasting evidence from the start as far as the correlation strength is concerned. For instance, pointing to weak correlation that no Mott insulator is found in the phase diagram of almost all these materials. There are also some little exceptions aside. There's hard detection of any upper bands in spectroscopies, and optics, looking at the reduction of the Drude part, the low energy part, points to a moderate correlation scenario. Whereas on the strong coupling side, we have bad metallicity, definitely, because we are in the range of milliohm centimeters as far as the resistivities are concerned. Strong sensitivity to doping and this varied phase diagrams typical of strongly correlated materials, and also we will see them evidences of local versus itinerant magnetism. So this gave rise to opposition between weak coupling and strong coupling theoretical scenarios. And here what you see also are the different evaluations from optics that placed these two red dots, the materials in the moderately correlated part of the ranges that we have. Whereas if you look at the Sommerfeld coefficients, you see them jumping around like crazy. So this was kind of difficult to rationalize. So from the outset, there were mixed evidences. Now, among the theoretical approaches, then there was one, and there is one very successful approach, which is based on completely itinerant electrons, and indeed this has to take into account the multi-orbital nature of these materials. And when one does the DFT calculation, discovered there are at least 5 bands So 5 bands coming from the 5 3D orbitals of iron at the Fermi level, giving rise to the conduction bands, with a dispersion of about 4 electron volts. They are populated by 6 conduction electrons, and they have partially lifted degeneracy of the orbital energies, but not with a big crystal field. So all the 5 3D electrons, 3D orbitals giving rise to the conduction bands are relevant at the Fermi level. But indeed, this scenario was quite successful and is quite successful. DFT, for instance, gives the correct Fermi surface topology, which is the one of semi-compensated metal with both electron hole pockets. And the nesting of the Fermi surface pockets provides both the necessary instabilities for SDW, so for the antiferromagnetic orders that one finds, and also spin fluctuations besides this, nearby these phases that can provide the superconducting pairing, which is found to be, the majority opinion is S plus minus in most of these compounds. So this seems successfully describing most of the evidences as far as the Fermi surfaces are concerned, and but still it has a few problems. And these problems are typically that LDA bands are 2 to 3 times too dispersive compared to what is measured by ARPES, for instance. That spin density, the LSDA, so the DFT calculations for the magnetic phases usually, unusually compared to what is known, overestimate the order of the ordered magnetic moments. So here you have all the different techniques predicting the magnetic phases, and so the order in the magnetic phase, and these are the experiments, so which are significantly below. And then that, for instance, a few of these materials which still has significant TC do not have any magnetic order around. Some others with even higher and the record TC, so the iron selenium monolayer has the claimed record TC of above 100 Kelvin, only have electron pockets, whilst other only have hole pockets. And there is also direct evidence of local moments in the paramagnetic phase from X-ray emission spectroscopy. So this can be seen as little problems to be adjusted, but this scenario is quite successful thus far. There is also, the analogy with cuprates in some respects. For instance, when you look from afar to the phase diagrams, these are cuprates, these are pnictides, you could see, so you could say these are pretty similar, and so led to theories based on the TJ model, actually TJ1, J2 model, because you need this kind of frustration to reproduce the magnetic orders, and this approach is quite successful in reproducing the magnetic orders. Still, one has some other problems, of which the most important for me is that here there is no Mott insulator, as it happens. Between the two magnetic phases, there is no Mott insulator to dope in order to use the TJ model. So one can tackle this from the DMFT point of view and similar approaches, so in a quite ab initio manner, and so include the multi-orbital interaction with the important role played by Hund's coupling, because we are talking about nearly half-filled multi-orbital, nearly half-filled 3D shells, so they are narrow and they're close to half filling, where all these configurations are important, and Hund's coupling wanting to align the spins is important. And even if the couplings have been calculated ab initio and are not huge, it is seen that these values of Hund's coupling do play a role importantly in these materials and in general in this kind of 5 3D electron compounds. So these are the results of the MFT from the Rutgers group, and indeed one sees different things. First, that overall, these are the mass enhancements. Overall, we are in more moderately correlated regime, so one finds actually 2 to 3 mass enhancement in general in the various families, and in the chalcogenides one finds even higher mass enhancement and big differentiation of the mass enhancement among the orbitals. This is actually was found, and it's a confirmation of something that we had predicted very early on at the beginning of the story of the pnictides, in which we realized that the electronic structure of the pnictides was the ideal playground for some mechanism for orbital-selective Mott transition and orbital-selective Mott physics that we had devised out of the effect of crystal field in systems with strong Hund's coupling. And this mechanism is basically based on the fact that the charge excitations in each orbital, which are ultimately responsible for the Mott physics for the electrons in each orbital, gets decoupled by Hund's coupling. This makes that, I mean, can be schematized in a very simple way. One thing that we have seen, even in Yerney's talk, is that one unavoidable effect of strong Hund's coupling is that for a half-filled shell, the Mott insulator is reached at very low interaction strength. So it's almost unavoidable. Now here we have 6 electrons on the average in the stoichiometric compound in 5 orbitals. So we are not half-filled, but we are nearby half-filling. So if one can expect to have an open gap at half-filling with spectral features aside from one another due to this Mott gap due to the half-filled Mott insulator, and be in the doped side of it. And in fact, all the orbital-selective Mott transitions in model that have been found thus far can be rationalized with this mechanism. And since the orbitals have charge excitations which are decoupled from one another, these excitations can be shifted from one another, and thus can be the gaps, the different gaps for electrons in the different orbitals, can be shifted to one another according, for instance, to the crystal field. And then, depending on on if your chemical potential falls within a gap or within a spectral feature for each orbital, you can have selective Mott states. For instance, here you will have the blue orbital having a metallic phase, and the red and black orbitals to be in an insulating phase. This, of course, can be even more, you can have even more varied phenomenologies depending on where the chemical potential falls, and also the fact that the Hubbard-like spectral features have different characteristics due to the individual features of the dispersion relevant for each orbital. So you can have different features in the spectra orbital resolved, and ultimately in systems in which you have all the complicated band structures of the pnictides, for instance, you have hybridization between the orbitals. But when the Hund's coupling is dominating, it is found that this structure of selective physics remains, and hybridization is a perturbation to it. So typically, it creates leaking in the spectra in a way that it's impossible to have a sharp gap for one orbital and a completely metallic phase for another. But still, it preserves a big difference in, let's say, the selective Mott phase is replaced by a very differentiated impact of correlation strengths among the orbital, even if it's not that clear-cut anymore. So in any case, this mechanism has been clarified subsequently, and even if from the outset phenomenological scenarios based on coexisting itinerant and localized electrons were also devised by different groups. There were also early experimental indications of this kind of physics, which I will not go through, but they were all found in 2011, 2012, and 10 from optical conductivity, having different Drude contributions, to ARPES seeing really different normalization for the different sheets of the Fermi surface, and so on and so forth. What I will here outline is the most recent experimental evidences, in which mostly in the chalcogenides, where we saw that the impact of correlations is even stronger, and so is the differentiation of such correlations, was, for instance, from the ARPES group of ZX Shen, the observation of temperature-induced crossover to an orbital Mott phase. Because we have seen in this electronic structures in which hybridization also plays a role of smearing the differences between the orbitals, the clear-cut orbital selective situation is replaced by a situation in which some orbitals have much stronger mass enhancement, and so they have lower coherence scales, whereas some others are more itinerant, more metallic, and have higher coherence scales. So that in temperature, it's possible to cross the lowest coherence scale for some orbitals and not for the others, and thus to observe what it was observed here, for instance, the loss of spectral weight in temperature for the dxy orbital, so for the Fermi sheet of mainly dxy orbital character, whilst the dyz of the more itinerant orbital spectral weight of the dyz here remain constant in temperature. And this was confirmed by terahertz spectroscopy, and also recently other investigations for iron, tellurium, selenium, or for high quality iron selenium monocrystal have showed a real differentiated impact of mass enhancement between these different orbitals at the Fermi level. And still, what is important is that it's always one of these, the XY orbital, which is consistently given more correlated as it was predicted by our simple mechanism. What we have done also thus far is trying to understand the impact in iron pnictides, which are a little bit less correlated than the chalcogenides, but still there is a clear signature of selective physics here. And one important thing also is to confirm that this scenario is one of the doped Mott insulator, the Mott insulator that one would have at half filling, is that the fact that the correlations are found extremely doping dependent. Something which was not seen in the previous DMFT calculations I've shown to you, because those were all compounds in which the correlation strength was varying due to the variation in kinetic energy, but those were all compounds at 6 electrons on average as filling is concerned. But indeed, pnictides are doped, and you can see across the doping phase diagram a huge variation of correlation strength. And here is what is actually calculated by our theory, which is also a DMFT-like approach. And here is the stoichiometric compound, and here is the whole doping, so approaching the half filling. You see that for all orbitals, these are the mass enhancements resolved in orbital. For all orbitals, the mass enhancements are growing, and the differentiation between them is growing too. And here is the extreme member of this 1 to 2 family, which has 5.5, so it's still half the way towards self-filling, 5.5 electrons, and is extremely correlated. And here are the experimental evidences collected, all I could find at the time, and it's a quite cluttered phase diagram here, but one has to remark these black dots, which are the Sommerfeld coefficients, so the specific heat derived mass enhancement for single crystal, which is clearly showing an increase up to almost 10 factor of 10. Whereas there are other evidences like optics, I've said, indeed, which seems showing much more of a moderate enhancement, or also this is the blue triangles here, or the orange squares are the global factor you have to put. Yes.
So the ARP has, so on the one on the left for the potassium,
yeah.
these ARP has these crosses or
yeah.
sides are for each individual sheet?
Yes, exactly. I was getting there. So here there are probes which are sheet resolved, which are these crosses. So orange for ARPAS and quantum oscillations are the red, the yellow crosses, whereas all the others are not resolved. So specific heat increases greatly. The optics, which is the blue triangle, rather saturates, and this is what I call ARPAS whole, is the square, also saturate, because this is the global factor that one has to put in front of the of the band structure to renormalize it. So why this is all interpreted in terms of coexisting strongly and weakly correlated electrons? Because one thinks a little bit, the specific heat is dominated by the heaviest electrons at the Fermi level, whereas the transport is quite naturally dominated by the lightest electrons. So it's why when you try to estimate the Mach enhancement from the two probes, you see them diverging if there is coexisting light and heavy electrons. Of course, if the renormalization factor is the same for all, then it factorizes in both of them and gives the same result. And this is the same for the whole band structure. Actually, the heaviest electrons, which are the one of the T2G orbitals, are dominant at low energy. So you have the stronger renormalization of the band structure at low energy. But since they are hybridized with the EGs, which are spread all over, then the renormalization of the whole band structure is just 2 or 3, even if at low energy you have much more squeezing of the bands. So this all is consistent with the fact that when you look at these resolved sheet by sheet mass enhancements, you see them here all concentrated, here much more spread, and here very much spread. So it all goes together, and it goes nicely with the theory as an evidence of weakly and strongly correlated electrons. Now, I have to rush, but this is some experiment that we have triggered because all these probes are low energy probes, are quasi-particle probes. So I wanted to see what happens at high energy, and these are X-ray emission spectroscopy that, I mean, I will not go into the details, but on different ways of doping with holes. So this is the same compounds doped with potassium, and these are doped with chromium at the place of iron. You see the local moment. This is a very fast probe, so you really see the paramagnetic local moment growing in magnitude with hole doping. And another interesting thing is that when you look at this extreme member here, it was found indeed to be to have a crossover in the, for instance, that you can see in the magnetic susceptibility, which is typical of the heavy fermion crossovers. Like here, you see the typical crossover in the same quantity from uranium, plutonium-3, and here from the first heavy fermion discovered in the D materials, which is lithium vanadium 204. So what is really nice is that it seems that we have put the hand on a mechanism that, since it can generate heavy and light electrons out of the D conduction bands, it's a way to generate a heavy fermion physics without F compounds, without F elements. So instead of F elements in which you have narrow orbitals from the outset, so those electrons are bound to come to be not very itinerant and need to be hybridized to become itinerant states. Here you generate heavy bands within the D manifold, coexisting with lighter bands within the D manifold, and so you have a recipe to create d-electron heavy fermions. So what is very nice is that this behavior can be controlled, and here you see Sommerfeld measurements from the Karlsruhe group for the whole doping of 1 to 2. You should just look at this blue curve here. And this is the theory. We have everything calculated from ab initio, and we just adjusted the Hund's coupling because this cannot be treated exactly in our simplified method. And then all the green point fall on the experiments without having to adjust parameters anymore, just showing how powerful is this mechanism in doping. And once so this is the extreme member, potassium, iron to arsenic 2. And once you do isovalent substitutions, these are the values found for Sommerfeld coefficient. So with rubidium and cesium instead of potassium, you are actually acting on the overall bandwidth, in-plane bandwidth, because you're squeezing the buccal plane. So you're getting the irons more and more apart. And the gamma grows up to almost 200 millijoule per Kelvin square, which starts being in the ballpark of heavy fermions. And here what is very nice is the theory follows without adjusting the parameters, just changing the ab initio band structures, follows, and here is what you get without interactions. So this is really the proof that these materials are indeed strongly correlated. And it seems that, so this is a general mechanism for controlling, and that we actually understand how it works, d electron heavy fermions. And now I have this question, which is for the second part of the talk. Can we also tune thermoelectric, thermomagnetic properties this way? So it seems completely unrelated, but I mean, you ask for an interdisciplinary talk, so you get interdisciplinary talk. So this is for something recent that I have done, and which you will see at the end it can be related. And so here's the proposal of a thermomagnetic setup or mechanism for doing self-cooling cables. So this comes out of the frustration of being so long in the superconductivity field without seeing the TC growing so much, even if these days still, I mean, we have some glamorous claims. But so one, in the end, out of frustration says, why not to get lower the ambient temperature, which is in some sense a triviality because it's what is done with cooling fluids. But a solid state mechanism that would do that, so make a device that could be operated from afar, could be really a nice thing. So what I thought one could exploit is the so-called Nernst-Ettingshausen effect. So everybody knows what is Peltier cooling. It is if you have a block of thermoelectric material, you make a current go through, and you get in the same direction a temperature gradient. What is less known is that the Ettingshausen cooling is the same thing that you do in a magnetic field. So you run a current perpendicularly to a magnetic field, and like in Hall effects, you get the effect, but in this case it's thermomagnetic, on the third perpendicular direction. So you get the temperature gradient in this direction. And these materials, like bismuth, metallic bismuth is the most efficient thermomagnetic material, are much less studied just because it's not very practical to include strong magnets in devices. So what I came up with is a mechanism. This is a section of a cable you can see here, and I just realized that if you have a high current cable carrying a strong current I here, it generates a magnetic field around it, which is just in the right geometry for a coating in thermomagnetic materials in which a much smaller current running can generate this gradient in the third perpendicular direction. You realize that the magnetic field is in the theta direction in this cylindrical geometry. The current running through the thermomagnetic coating is in the z direction, and so you have in the third direction a temperature gradient. Indeed, here you need an insulation between the two layers, but so calculations can be done for this setup. I just want to say a few simple things here. So you have three players in the materials that act in this mechanism. One is the Nernst coefficient. This is the good guy trying to, so it measures the effect of extracting the heat. Then there's the bad guy, which is the thermal conductivity term, which wants to bring the heat back. And then there is a very bad guy who is Joule heating. So resistivity is bad, and because it generates heat. Of course, it's a thermodynamic machine, so you don't get free lunch. So you get to extract more heat than what you actually need. So these are typically these are measured in what's called the thermomagnetic figure of merit, and which gives the performance of each material. And there is one observation that has to be made, is that the good effect is linear in the current, whereas the very bad guy is quadratic. So it means that you get a maximum of the effect, and you cannot just put all the current you want to get all the heat extraction you want. So there is indeed a maximum temperature difference that you can get with, for instance, it was calculated for a rectangular block, and it's actually measured by this, exactly proportional to this figure of merit. So the higher the figure of merit, the higher the temperature drop. And for a rectangular cooler in bismuth was estimated in the 60s at 30 Kelvin, but then you have some tricks that are used in thermoelectricity. Typically, one is of cascading devices that gets you lower and lower temperature drops, I mean, to higher temperature drops, so to much more and more cooling. This is because you can stack devices which has increased cooling power at each layer. For the thermomagnetic devices, this is even cooler because you just need to shape the device. And since the heat, the part in which you extract the heat is smaller than the heat sink face, you will have increased cooling power when you go through the device. This was done, and such a device was experimented still in the 60s, and they got for here you cannot really read, for 11 Teslas to 100 Kelvin of temperature drop. So we can expect some of these this geometrical effect to be here in the circular geometry, because you have an external phase, so an heat sink phase, which is actually larger than the heat source phase. So indeed, then one can also think of stacking different devices and also exploiting the stacking of this used in thermoelectricity. So calculations can be done for these materials, of course, taking into account the fact that the magnetic field decreases with the radius. These are the equations, the linear responses come out of Onseger-Cullen theory of thermoelectric effects near equilibrium, and then you have also to enforce energy conservation at each point, and then you can solve for heat and temperature distribution. I will not go through these details. I just want to show you that the formulas for this circular geometry are very much alike the formula known for the rectangular geometry. In two things are the same. So they're just changed by these geometrical factors, which are actually decaying factors, log decaying factors. And so which means that the maximum temperature drop that can be reached is similar, is reduced. So this for the rectangular cooler is the flat line, and this is both numerical and analytical solution of the circular geometry. So you see this is reduced actually. Why is this? This is because the decay of the magnetic field, unfortunately, supersedes the effect, the gain of the circular geometry. However, and these results are just plotted as a function of the thickness of the cooler. So this is big radius over small radius. However, what is very nice is that if you put B constant, so the constant magnetic field artificially here, but it will come handy, you see that the effect actually grows. So this is the geometrical effect that I was mentioning, which is unfortunately superseded by the decaying magnetic field. So now I'm getting to conclusion. Just what I want to show is that then the other important result is that for very small thickness, this gets to 1, so you get the maximum cooling, maximum temperature drop, but this gets to infinity. So you also get the electric field you have to apply gets to infinity. So you have to decide and find a compromise between a too thin cooler in which you have the maximum temperature drop, but you spend a lot of energy, and a large enough cooler in which you have less energy spent, but less temperature drop. So and this comes directly out of the analytical results. Now, the important thing is that all these analytical results were derived for constant coefficients, which is not. These are the real coefficients for bismuth. So one has to implement a numerical solution, which is in the next slide. But what is also nice is that this is the ZT, so is the figure, the adimensional figure of merit of bismuth, and it is seen to saturate at high enough magnetic field, which is really important for us, because if you can manage your device to be all in high magnetic field, then its properties will be insensitive to the decay of such magnetic field, and you will have the geometrical enhancement of the cooling. And these are the numerical results. Here in yellow you see for realistic parameters of bismuth, here you see that you get up to 60 Kelvin of temperature drop. So this is the enhancement due to the fact that if the device is thin enough, this is for a typical magnetic field of 12 Tesla around the cable, if it's thin enough, then it grows, and then it's only after the fact that the border of the device starts being in the lowest part of the magnetic field you get the decay, the logarithmic decay that is foreseen, it is predicted from the analytical model. And what is even more interesting is that, and this is obtained for an expelled heat of 80 watt per centimeter, which is still pretty big. So I'm not sure this is convincing for technological applications, but it's encouraging. And what is interesting is that if you, when you look at the formula for a finite heat load, so this is the formula for a second stage, for instance, in which the first stage say diverses his heat, then you have a way of maximizing the temperature drop of the second stage, which is to minimize the thickness of the second stage. And in fact, you can make a large first stage and a thin second stage, and you get as high as 100 Kelvin, more than 100 Kelvin as temperature drop. So this is, but unfortunately, this is done with 1,000 watt per centimeter expelled, so this is not very convenient. So just one last slide to show what is the link. So these are the little problems that can be discussed about this setup, but what is the link with what I showed before? Where it happens that among the best and future, maybe future thermoelectric and thermomagnetic materials explored are heavy-fermions. So these are some known thermoelectric heavy-fermions, and is maybe less known, but besides bismuth, which is definitely the best, there are all heavy-fermions explored for thermomagnetic and Nernst effects. And this, in some range of temperatures, even if the Nernst effect is much below, the figure of merit is much above that of bismuth. So it depends on, but unfortunately for heavy-fermions at pretty low temperatures. So the question is, can we improve thermoelectric, thermomagnetic performances with our mechanism for creating d-election heavy-fermions, in which these scales are less extreme, indeed, so they will be less heavy, but it will happen also at less low temperature. Okay, so these are my conclusions, and thank you for your attention.